The Mersenne Twister is a pseudorandom number generator. It is, by far, the most widely used PRNG. Its name derives from the fact that its period length is chosen to be a Mersenne prime. The Mersenne Twister was developed in 1997 by Makoto Matsumoto and Takuji Nishimura. It was designed specifically to rectify most of the flaws found in older PRNGs. It was the first PRNG to provide fast generation of high-quality pseudorandom integers. The most commonly used version of the Mersenne Twister algorithm is based on the Mersenne prime 219937-01. The standard implementation of that, Montana 19937, uses a 32-bit word length. There is another implementation that uses a 64-bit word length, Montana 19937-64. It generates a different sequence. Adoption in software systems. The Mersenne Twister is the default PRNG for Python, Ruby, IDL, Free Pascal, PHP, Maple, MATLAB, Gauss, Julia, CMU Common Lisp, Microsoft Visual Studio, the GNU Multiple Precision Arithmetic Library, and the GNU Scientific Library. It is also available in C++ since C++11. Add-on implementations are provided by the Boost C++ libraries, glib, and the NAG numerical library. The Mersenne Twister is one of two PRNGs in SPSS, the other generator is kept only for compatibility with older programs, and the Mersenne Twister is stated to be more reliable. The Mersenne Twister is similarly one of the PRNGs in SAS, the other generators are older and deprecated. Advantages. The commonly used version of Mersenne Twister, Montana 19937, which produces a sequence of 32-bit integers, has the following desirable properties. It has a very long period of 219,937 AAA1. While a long period is not a guarantee of quality in a random number generator, short periods can be problematic. It is K-distributed to 32-bit accuracy for every 1 per mil currency Ka per mil 623 currency. It passes numerous tests for statistical randomness, including the die-hard tests. Disadvantages. The state space is too large and needlessly stresses the CPU cache. In 2011, Saito and Matsumoto proposed a tiny version of the Mersenne Twister to address this issue. The tiny version, TinyMT, uses just 127 bits of state space. By today's standards, the Mersenne Twister is fairly slow, unless you use the SFMT implementation. It passes most, but not all, of the stringent test U01 crush randomness tests. It can take a long time to start generating output that passes randomness tests, if the initial state is highly non-random particularly if the initial state has many zeros. A consequence of this is that two instances of the generator, started with initial states that are almost the same, will usually output nearly the same sequence for many iterations, before eventually diverging. The 2002 update to the MT algorithm has improved initialization, so that reaching such a state is very unlikely. K-distribution. A pseudorandom sequence I of W-bit integers of period P is said to be K-distributed to V-bit accuracy if the following holds. Let T a UNCV, X, denote the number formed by the leading V bits of X, and consider P of the KV bit vectors. Then each of the two KV possible combinations of bits occurs the same number of times in a period, except for the all-zero combination that occurs once less often. Alternatives. The algorithm in its native form is not suitable for cryptography. The reason is that observing a sufficient number of iterations allows one to predict all future iterations. A pair of cryptographic stream ciphers based on output from the Mersenne Twister has been proposed by Matsumoto, Nishimura, and co-authors. The authors claim speeds 1.5 to 2 times faster than advanced encryption standard encounter mode. An alternative generator, well, offers quicker recovery, and equal randomness, and nearly equal speed. Marseglia's XOR shift generators and variants are the fastest in this class. Algorithmic detail. For a k-bit word length, the Mersenne Twister generates integers in the range 0 to car 2. The Mersenne Twister algorithm is based on a matrix linear recurrence over a finite binary field F2. The algorithm is a twisted generalized feedback shift register of rational normal form, with state bit reflection and tempering. It is characterized by the following quantities: W word size, N, degree of recurrence, M, middle word, or the number of parallel sequences, 1 a per mille currency M a per mille currency N, R, separation point of one word, or the number of bits of the lower bitmask, 0 a per mille currency or a per mille currency W, 1, A, coefficients of the rational normal form twist matrix, B, C, TGFSR, R, tempering bitmasks, S, T, TGFSR, R, tempering bit shifts, U, L, additional Mersenne Twister tempering bit shifts, with the restriction that 2NWAA1 is a Mersenne prime. This choice simplifies the primitivity test and K-distribution test that are needed in the parameter search. For a word X with W bit width, it is expressed as the recurrence relation, with as the bitewise OR and as the bitewise exclusive OR, ZOO, XL being X with upper and lower bitmasks applied. The twist transformation A is defined in rational normal form, with INA AA1 as the A, NA AA1, identity matrix. The rational normal form has the benefit that it can be efficiently expressed as where. In order to achieve the 2NWAA1 theoretical upper limit of the period in a TGFSR, IB, T, must be a primitive polynomial, IB, T, being the characteristic polynomial of. The twist transformation improves the classical GFSR with the following key properties: period reaches the theoretical upper limit 2NWAA1, equidistribution in n dimensions, as like TGFSR, R. The Mersenne Twister is cascaded with a tempering transform to compensate for the reduced dimensionality of equidistribution, which is equivalent to the transformation or equals RA or equals at R1 RT, T invertible. The tempering is defined in the case of Mersenne Twister as Ya equals Za Asha, Za AU, Ya equals a Ya Asha UAS, A and AB, Ya equals a Ya Asha UAT, A and AC, Za equals Ya Asha, UAL, with, as the bitewise left and right shifts, and as the bitewise AND. The first and last transforms are added in order to improve lower bit equidistribution. From the property of TGFSR, is required to reach the upper bound of equidistribution for the upper bits. The coefficients for Montana, 19937R, W, N, M, R, A equals A, 32, 624, 397, 31, or equals A 9908 BODF 16, way equals A11, S, B, A equals A, 7, 9D2C 568016, T, C, A equals A, 15, EFC 600016, Li equals A18, a small lagged Fibonacci generator or linear congruential generator usually is used to seed the Mersenne Twister with random initial values. Pseudocode. The following piece of pseudocode generates uniformly distributed 32-bit integers in the range 0, 232 AAA1, with the Montana 19937 algorithm. Create a length 624 array to store the state of the generator, int, 0623, mt, int index equals 0. Initialize the generator from a seed, function initialize generator, int seed, index, equals 0, mt, 0, equals seed, for I from 1 to 623 loop over each other element, mt, I, equals lowest 32 bits of 1,812,433,253 plus I, 0x6C0789665. Extract a tempered pseudorandom number based on the index th value, calling generate numbers every 624 numbers, function extract number, if index 0, generate numbers. Int y, equals mt, index, y, equals yzor, y, equals yzor and 0x9D2C5680, y, equals yzor and 0xEFC60000, y, equals yzor. Index, equals mod 624, return y. Generate an array of 624 untempered numbers, function generate numbers, for I from 0 to 623, int y, equals bit 31 of MT, I, plus mod 624, and 0x7ffffff, bit 0 to 30 of MT. MT, I, equals MT, I plus 397, mod 624, XOR, if equals 0 y is odd, MT, I, equals MT, I, XOR 0x9908 BODF. SFMT, SFMT, the SIMD-oriented fast Mersenne Twister, is a variant of Mersenne Twister, introduced in 2006, designed to be fast when it runs on 128-bit SIMD. It is roughly twice as fast as Mersenne Twister. It has a better equidistribution property of v-bit accuracy than MT but worse than well. It has quicker recovery from 0x's initial state than MT, but slower than well. It supports various periods from 260701 to 2,216,09101. Intel SSE2 and PowerPC Altiv are supported by SFMT. It is also used for games with a CellBE in the PlayStation 3. MTGP is a variant of Mersenne Twister optimized for GPUs published by Mitsuo Saito and Makoto Matsumoto. The basic linear recurrence operations are extended from MT and parameters are chosen to allow many threads to compute the recursion in parallel, while sharing their state space to reduce memory load. Sample code 1 for CUDA includes parameter sets suitable for 256, 512 and 1024 parallel threads per block, and up to 200 blocks generating independent random streams. The paper claims improved equidistribution over MT in performance on a high-specification GPU of 4.7 milliseconds for 5x107 random 32-bit integers. References. External links, the academic paper for MT, and related articles by Makoto Matsumoto, Mersenne Twister homepage, with codes in C, Fortran, Java, Lisp and some other languages, SFMT in action the Code project.